We've talked about joint distributions of two discrete random variables. But what if we want to study the relationship between two continuous random variables? The flower duet that you've been listening to, like the Beethoven violin sonata from a previous video, is about the delicate relationship between two different parts. But each voice in the flower duet is more fluid, more continuous than the violin and piano in a violin sonata. The tools for analyzing the relationship between two continuous random variables differ slightly from the tools for discrete random variables, as you will learn in this video. Earlier, we saw that the joint distribution of two discrete random variables, x and y, could be described by the joint PMF, which tells us the probability that x and y equal particular values. The joint PMF could be expressed in two ways, either as a table or as a function. Similarly, the joint distribution of two continuous random variables is described by something called the joint PDF, which is also a function of two variables. Notice that we use parentheses for the joint PDF as opposed to square brackets for the joint PMF. Unlike the joint PMF, the values of the joint PDF do not correspond to probabilities directly. That's because for a continuous random variable, the probability that a random variable equals any particular value is always 0. To get probabilities from a joint PDF, we have to integrate it, just as we did with the PDF. Since the joint PDF is a function of two variables, we can think of it as a surface floating above the xy plane. Suppose we want to know the probability that the random variables x and y fall in some region. Let's call that region B. To calculate the probability of B, we have to calculate the volume under the joint PDF at B. This will involve a double integral since we have both x and y variables. This volume corresponds to the probability that we want. Now let's compare the discrete and continuous versions of various formulas for working with joint distributions. If we want to calculate the probability that our random variables fall in some region B, in the discrete case, we would calculate the sum of the joint PMF over all x and y that are in B. Now there's some work needed to work out the limits for this double sum, but this is the general idea. In the continuous case, the double sum is replaced by a double integral, and the joint PMF is replaced by joint PDF. We'll give an example of how to set up one of these double integrals in just a minute. We might also be interested in the marginal distribution of x. To calculate the marginal distribution of x from a joint PMF, we have to sum over all possible values of y. Likewise, to calculate the marginal distribution from a joint PDF, we have to integrate over all the possible values of y. The marginal distribution of y works similarly. In the discrete case, we have to sum the joint PMF over all the possible values of x, so the resulting function is only a function of y. In the continuous case, that sum becomes an integral, and the joint PMF is replaced by a joint PDF. Let's do an example together. Suppose there's a company that produces cans of mixed nuts containing almonds, cashews, and peanuts. Each can is exactly 1 pound, but the amount of each type of nut is random. The joint PDF of the amount of almonds, which we'll call x, and the amount of cashews, which we'll call y, has the following joint PDF. We want to know the probability that a particular can will have more almonds than cashews. First, let's express this event in terms of our random variables x and y. We want to know the probability that the amount of almonds x is greater than the amount of cashews y. We're going to need a double integral over the joint PDF, but what should the limits of integration be? For this outer integral, which is over x, we'll integrate over all possible values of x, which is from minus infinity to infinity. Of course, if you actually look at the joint PDF, it's actually 0 over most of this range, but we'll take care of that later. Now, for the inner integral, we need to figure out the values of y that satisfy our event of interest. For a given value of x, we need all values of y less than x. So we need to integrate y from minus infinity up to x. Now right now, this integral is not in a form that would be easy to type into a calculator, because p of x and y is this piecewise function. So let's try to simplify this first. We know that p of xy is equal to the simple function 24xy when x is between 0 and 1, and when y is between 0 and 1 minus x. Now notice I combined these last two constraints here. This last constraint can be rewritten as y is less than or equal to 1 minus x. But if x is between 0 and 1, then 1 minus x will be automatically less than 1. So I don't need to worry about this constraint that y is less than 1. So I'll just write this as y has to be between 0 and 1 minus x. Now, let's see if we can rewrite this double integral in terms of just 24xy, the simple function here. It's pretty clear that the outer integral over x will go from 0 to 1. This inner integral over y is supposed to go from 0 to x, but we have to be careful, because we have to be careful that y does not exceed 1 minus x. Let's break this into a few pieces. When x is between 0 and 0.5, then x will be less than 1 minus x. So as x ranges from 0 to 0.5, we can actually integrate 24xy from 0 all the way up to x. On the other hand, when x is between 0.5 and 1, then we actually have that 1 minus x is less than x. So as x ranges from 0.5 to 1, we don't quite make it all the way up to x for y. We have to stop at 1 minus x. So we only integrate y from 0 up to 1 minus x. As far as I'm concerned, at this point, you are completely done. These integrals are now in a form that can be easily plugged into a calculator. Everything up to this point required careful human thinking, but everything after this point is purely mechanical. So it's not a big deal to me if you don't know how to evaluate this double integral, since in practice, you would probably just type it into a calculator. But let me quickly review the basic idea of how to evaluate these double integrals for those of you who are interested, but feel free to tune out. Now, let me contrast evaluating a double integral with setting up the double integral. To set up this double integral, we started with the outermost integral over x and worked our way inwards. Now to evaluate the double integral, we're going to start with the innermost integral and work our way outwards. Now this innermost integral is over y, even though there are still x's in the expression. No worries, just treat the x's as if they were constants. So we can even bring the 24x outside of the integral, and then integrate y dy. So that integral turns out to be 24x times x squared over 2. Notice that the resulting expression is a function of x only. That's because we integrated over all the possible values of y. Now let's do the same thing for this other double integral. Again, we'll start with the innermost integral, which is over y. We'll treat all the x's as constants and do this integral. And we get this expression for the integral. Now at this point, it's really easy to evaluate these integrals. These are just single variable integrals over x. And if you evaluate these, you get 0.5. So there's a 50% chance that you get more almonds than cashews, and a 50% chance that you get more cashews than almonds? In hindsight, this answer was obvious. If you look at this joint PDF above, it's completely symmetric in x and y. That is, if you swap the roles of x and y, you get the exact same expression. So there should be no reason for one to be greater than the other. Just now, we set up the double integral for this probability using a purely algebraic approach by manipulating these inequalities. I wanted to also present a more geometric way of arriving at that same set of double integrals. Let's imagine a bird's eye view over the xy plane. Let's first sketch the region where this joint PDF is non-zero. It's non-zero when both x and y are between 0 and 1, and when x plus y is less than or equal to 1. That region is shaded in green here. Notice that this upper boundary is the line x plus y equals 1. Now let's shade the region corresponding to the event of interest, where x is greater than y. That region is shaded in orange here. So we need to integrate 24xy over the intersection, the overlap between these two regions. And that's this triangle here. So how do we integrate 24xy over this triangle? So when x is between 0 and 0.5, we have to integrate y from 0 up to x. And that's shown here. On the other hand, when x is between 0.5 and 1, we have to integrate y from 0 up to 1 minus x. And that's shown here. And if you compare this with the previous slide, you'll see that this is the exact same set of double integrals we obtained earlier.